So last day, if you weren't here, I do recommend checking out that video from Thursday's class. That would be week 13, class number 3. We learned how to name alcohols, and there weren't a lot of people here on Thursday afternoon, but it's very easy. So I would recommend maybe tonight or, in the next couple days watching last week's video, week 13, lecture 3. But today we're going to move into the properties of alcohols, and this is kind of what your lab is about tomorrow. So alcohols we learned back way back in chapter 1, alcohols have the functional group OH. Okay, so all an alcohol is a chemical that has a functional group of OH. The boiling point of an alcohol is always higher than that of the analogous alkane. Now that's a word you guys might not be familiar with, but it's definitely a word you might see on your final. What do I mean by analogous alkane? Well, it's the same carbon length. So what I mean is, like, if I asked you guys to compare propane versus to propanol, okay, it ends in OL because it's an alcohol. This would be an analogous alkane. It's the same number of carbons, 3 carbons, but it has an alcohol on it. Okay, another example would be like, say, cyclohexane versus cyclohexanol. Sorry about that. Okay, so if I have a 6 carbon chain, but I put an alcohol on it, the boiling point gets much higher, and you'll kind of look at this tomorrow. Now, why is the boiling point higher? Well, you actually learned about this long time ago, back in chemistry 1120, if you can remember back that far ago. Chemistry 1120. You guys learned about intermolecular forces. And the more intermolecular forces you have, the higher the boiling point. So alcohols have the ultimate intermolecular force, hydrogen bonding. Remember, now this, I'm not going to ask you about hydrogen bonding, like to explain it or anything. That was chemistry 1120. So not really something I care about. Sorry, guys. Hold on one second. Okay, so when I say hydrogen bonding, the only thing I would worry about is if I asked you why is an alcohol, or why doesn't alcohol have a higher boiling point, it's because of hydrogen bonding. That's it. You don't need to explain what it is. If you are curious, hydrogen bonding is what happens when you have a hydrogen in a compound that's bonded to F fluorine, O oxygen, or N nitrogen. So FON. Okay, so the reason the boiling point is higher is because alcohols have hydrogen bonding intermolecular forces. The more intermolecular forces you have, the more energy it takes to break the bonds, meaning it would have a higher boiling point. Alkanes only have London dispersion, which it's typically called van der Waals dispersion, but I think in your case in chemistry 1120, you learned about London dispersion. Alkanes are not polar, they have weak intermolecular forces. So simple reason is, why is there a higher boiling point in alcohols? Hydrogen bonding. That's it. Full stop. That's all you need to know. Honestly, most of the weird behavior in many chemicals is usually due to hydrogen bonding. So if I ever asked you, why does water have a high boiling point? Why does water have a high heat capacity? It's always because of hydrogen bonding. So this is an interesting one, and you'll see this tomorrow in the lab. This is definitely, I find this so cool. What about solubility of alcohols? Okay, so when I say solubility, I mean, like, do they dissolve in water? Do they dissolve in not a polar thing, non-polar thing, sorry, like alkanes. Well, small alcohols are completely soluble in water. When you mix them together, it just makes a single solution. Now, what do I mean by a small alcohol? I mean something like methanol, ethanol, propanol, small carbon chain, right? So like ethanol is one of them. Isopropyl alcohol you can get at the pharmacy here. It's a good disinfectant. Actually, most of the things we've been using for the last few months to disinfect from coronavirus would have some form of small alcohol in it, dissolved in water. And then there's typically like sometimes there's things that make it foam or make it gel, but and some things that make it smell nice. But yeah, these small alcohols are completely soluble in water. But, and this is where it gets interesting, when you have a long hydrocarbon with an alcohol on it, the solubility can decrease. So after about 4 carbons, when you get to like pentanol, hexanol, heptanol, octanol, the solubility is decreased. It's noticeable, and you might see 2 layers. Now, why is that? Okay, this goes all the way back to, well, I shouldn't say all the way back. Hey, this goes back to last week where we learned about surfactants and soap. Soaps are these giant molecules, or I guess I should say surfactants, are these giant molecules that have polar and non-polar ends. Well, when an alcohol gets so big, it can really be the same type of thing. The reason why the solubility decreases as hydrocarbons get longer, it requires more energy to overcome these hydrogen bonds between the alcohol molecules, as the molecules are very tightly packed and their size and mass increases. In other simple words, when the chain is so long, so imagine I had something like this, right? Like this giant carbon chain here. Well, this part of the chain kind of acts as a nonpolar substance. This part of the chain acts as a polar substance, and they just do not mix with water. This part doesn't want to mix with the water. Sorry, I got a question in the chat there. That's a good question, I'm going to say no, but that's a great question. Let me just see. Okay, so let me kind of explain my thought process here. So Naim's question are all alcohols liquid in nature? And I know methanol, ethanol, propanol are definitely liquids. But my rationing or my reasoning here is once the hydrocarbons get so big, once the molar mass and size gets so big, I would imagine that there are solid alcohols out there. And I bet you most alcohols are colorless liquids, but there are definitely, yeah. So like an example of a solid alcohol would be cetyl alcohol. This would be C16H34O. Its hydrocarbon chain is so big, it tends to be waxy. So that would be an alcohol that's a solid. Okay, cetyl, C-E-T-Y-L. But Naim, you bring up a very good point, though. Like especially in the chemistry lab, in industry, most alcohols are solids, or sorry, most alcohols are colorless liquids at room temperature, and they can be solid. Typically, they're solid when the chain gets so long. Okay, so and again, back to this slide, solubility decreases when the hydrocarbon chain increases, is it takes a lot more energy to overcome this hydrogen bonding. The other reason is the chain here has a giant nonpolar end to it, which doesn't want to mix with water. Remember, water mixes with polar things. Okay, this this slide 20, you don't need to know for your exam. but you might need to know this for your lab tomorrow. So let's kind of talk about acids and bases. I'll talk about primary, secondary, and tertiary. And then basically, if I can get to the end of alcohols, we'll probably be pretty good for today. We'll see how much we can do. We don't really need to do all of chapter 6 for your final exam, but we did section 1 and section 2. So we did halogens and alcohols. That is definitely on your final. So yeah, let's get through alcohols today. Okay, so alcohols, like water, can be both weak bases and weak acids. And this is kind of going back to what you guys did in CH2420. The Ka, the acid ionization constant, so the strength of the acid. Remember that, the equilibrium constant? I don't know if you guys remember that from 1121, but it's very similar to that of water. It's just slightly less. So the order of acidity of alcohols is typically water would be a little stronger, then primary, then secondary, then tertiary. I'm only showing you this for the lab tomorrow. So not on exam, but yes, in your lab. So let's just look at this. And actually, this is something that you should know from an earlier chapter, this concept of primary, secondary, and tertiary. We did this back when we were doing naming. We talked about like tert, butyl, sec, butyl. So we've actually did this back in unit 2. Okay, so let's look at these terms. Primary alcohols. Primary alcohols are when the carbon atom that has the OH is attached to only one other carbon. So here's my alcohol. I have the carbon and I have the oxygen or the OH here, and it's only attached to one other carbon. We call that primary. Secondary alcohols, so my carbon is here. This is the carbon that's attached to my OH. It's attached to 2 other carbons. And tertiary is exactly what you would imagine. It's a carbon with an alcohol group on it that's attached to 3 other carbons. Okay, so primary alcohols are alcohols attached to one other carbon. Secondary are alcohols attached to 2 other carbons, and tertiary are alcohols attached to 3 other. Now remember, when I say alcohols, I am including the carbon the carbon it's bonded to. Whoops. I meant to choose my highlighter, sorry. So like I'm including the carbon here. Okay, and the strength of it goes, water is stronger, is more acidic than its primary, secondary, and tertiary. So the weakest acid here, the weakest, or the smallest Ka would be tertiary. So, well, let's look at this example. I was just going to write here, in terms of strongest, this would be the most acidic. In terms of alcohols, this would be the least acidic. Okay, so you might see this in the lab tomorrow, which alcohol would be the most acidic. So remember, water is number 1, then it goes primary alcohols, then it goes secondary alcohols, and then it goes tertiary alcohols. So I need to look at these 2 chemicals and figure out which one, like, is it primary, secondary, or tertiary? So first things first, let's get my highlighter out. No, I'm not going to use purple. That's a bit dark. Let me pick another color here. So first of all, this is kind of what I'm not counting. The carbon where the alcohol is bonded to doesn't get counted. What I do need to do is look at the carbons that are attached to that particular carbon. So I have a carbon here and a carbon here, and I need to ask myself how many carbons are attached to each of these. So let's look at the left one. It's attached to, let's pick another color, 1, 2. This would be a secondary alcohol. This one is only attached to one other carbon. So this would be a primary alcohol. So if I asked you, like in the lab tomorrow, which do you think would have the most acidic properties? Remember, most acidic would have the lowest pH. Well, it would be the secondary one, this one. And the reason is secondary alcohols are weaker than primary. This is my list up here of the order of how strong they are. So water would be a little stronger, then it's primary, secondary, and tertiary. So 2 is weaker than 1. So, so I guess, sorry, I'm saying which would be the most acidic. It would be this guy. Primary alcohols are more acidic than secondary. All right, cool. So you're going to look at that a little bit more in detail in the lab tomorrow. All right, do you guys have any questions on that before I kind of finish off alcohols? I just want to talk about what type of alcohols you might see in the industry, and then that'll be pretty much it for today. We're almost done. Any questions, or can I move on? Pretty quiet. It's been a long semester. There's only a few of you here today. All right, so last part, alcohols as additives. Where would we use alcohols? Thank you, Naim. Where would we use alcohols in real life or in industry? You know, what's the purpose of this? Well, alcohols can be added to help things combust, for example, but another additive or another reason we would look at alcohols in oil and gas industry, and this is a good thing to know, wink, wink. See if I can draw a winky face here. Whoa, messed up winky face. Is alcohols can actually act as defoaming agents. Okay, so first, what's a foam? A foam we talked about in chapter 5. A foam is when you have gas dispersed in a liquid medium. So think about petroleum. Petroleum is predominantly liquid, but it can have trapped gas in it. So that trapped gas can, when it's agitated, can form foam. Kind of like when you think of foam, think of like if you shake up a Pepsi or Coke or 7 Up and all that gas kind of rises to the top, that's foam. And alcohols can help reduce the foam in industrial process liquids. So anything that is added to reduce foam, to reduce the formation of foam, is called a defoamer. And fatty alcohols, now when I say fatty, I mean long carbon chain. So fatty means long carbon chain. Alcohols that have a long carbon chain can actually act as like a stabilizer to reduce the foaming. They can reduce the emulsion between the oil and gas. So they were typically added to oil products to boost the efficiency. Foams aren't going to burn as well as liquids. Foams aren't going to be pushed through pipelines as well as liquids. You do not want foams, right? Think about if you pumped gas into your car, or sorry, petrol into your car, and it was full of gas. It was foamy and bubbly. It wouldn't combust very efficiently. It would be very dangerous, actually. So alcohols can be added to oil and gas products traditionally to reduce foam. There are other types of defoamers as well. It doesn't need to be alcohols, but they typically are alcohol-based. Oil-based defoamers typically have some sort of oil component or non-polar component, meaning like something waxy or hydrophobic. Remember, oils or hydrocarbons are hydrophobic. They are not attracted to water. So typical waxes, you do not need to know any of this, don't worry, but typical waxes could involve long carbon chains that have an OH functional group. Okay, so Defoamer additives added to oils are typically oil-based. They're waxy, they're hydrophobic, they might have alcohols on them, and they might also have a surfactant to make sure that the oil and, say, gas molecules are being emulsified or mixed together. Okay, heavy duty defoamers are usually used for knocking down surface foam. So again, surface foam, you can think of like shaking up a Pepsi and you get all that foam on the top. That is not good, right? Foam is not easy to pump through pipelines. It's not efficient for burning. So a good way to get rid of that is to add surfactants and defoamers. There are, of course, also water-based defoamers. They're different than the oil and wax ones. Their oils are mineral oils or vegetable oils, but they still contain fatty alcohols in them. So really the only thing you need to know here, wink, wink, is if I asked you what chemical could be added to defoam, reduce the foam in a petroleum mixture, you hopefully would say alcohols can be used. Typically, and for like a perfect answer, you could say a fatty alcohol or a long chain alcohol, but they are typically used to reduce air trapped in your oil. So again, if I ask you what chemical to use to defoam or reduce foam, I would hope you would say an alcohol, or more specifically, a long chain alcohol. They call them fatty. So like when you hear the word in nutrition like fatty acids, they're talking about long carbon chains. Ethers, anti-knock. I'm just trying to think of what else I want to do the other day for the, I think, okay, whoops. I think I'm going to finish for today. Whoops, I didn't mean to stop that. There's two topics I want to finish, and we can finish this. Well, I guess I could do one of these right now and get it out of the way, and then we could have more time for review. Okay, let's do that. So guys, there's two things left in chapter 6 I want to do. I want to talk about anti-knocking, and then at the very, very end, I want to talk about, I'm going to skip a lot of this, don't worry, but I want to talk about sweetening, which I'll save for Wednesday's class. I want to talk about how amines can use for sweetening. It's only maybe 5 or 6 slides. So there's one thing I want to mention for you right here, and then I'll finish it off at this. I'm just going to very quickly do ethers. There's one important property of ethers I want to talk about, and then halas, we're finished. And the reason I'm squeezing this in now is, one, it's only 4 o'clock, and two, the more I get done today, the more review we can do for your final on Wednesday or Thursday. So for your final exam, you definitely want to know 6.1 and 6.2. 6.1 was halogens, and 6.2 is alcohols. There's only one thing from 6.3 I really want you to know, and it's about this concept of anti-knocking. Okay, so first things first, what is an ether? Just a reminder of chapter 1. A molecule, an ether is a molecule that has typically well, not typically, always an oxygen within that carbon chain. Ether molecules are typically polar. They do have lower boiling points. Yes?
Can you share your screen, please?
Oh, sorry. Yes, I can. Thank you for letting me know.
Okay, no problem.
When I exited the PowerPoint, I guess I didn't reshare my screen. Well, that means I'm going to have to go back a slide. Sorry. Here, I wrote this down. On your final chapter, or section 6.1 was about halogens. Section 6.2 was about alcohols. They're good to know. For section 6.3, I just want you to know about one thing, and it's the anti-knocking part, which I'm going to do in a second. It's an engine additive, typically added to, obviously, petroleum or petrol products. So ethers, they look like this. They are typically polar. They don't quite have the boiling point of alcohols because there's no hydrogen bonding, but they do have similar solubility as alcohols. You do not need to know this. What I do want you to know is this part. Okay, so what would be the purpose of an ether? Well, a purpose of the ether, of an ether, I should say, is an anti-knocking agent. So first of all, what is MTBE? MTBE is methyl tert butyl ether. You don't need to memorize that, don't worry, but MTBE is a gasoline additive. And what it does is it adds oxygen to gasoline or petrol, and it increases the octane number. Okay, very, very, very important for your final exam. We talked about octane number back in chapter what? 2? I think we talked about it again in chapter 5. Octane number or octane rating is related to the efficiency of how your gasoline or petrol burns. The better the number, the better the rating, the better the quality, the cleaner the combustion, the more efficient your fuel is. So MTBE, methyl tert butyl ether, is an agent added to gasoline to reduce engine knocking. Now, engine knocking is the temperature it takes to combust the air fuel mixture in your car. So the way that your car works, I say car, I mean your vehicle, whatever you drive, there's a mixture of air and fuel pumped through your vehicle, which needs to be sparked and ignited. And adding this anti-knocking agent by increasing the oxygen, it helps the air fuel mixture ignite or spark. And what this does is we in engine terms is it reduces knocking. It lowers and helps the combustion temperatures for your fuel in your car. In simple words, the bottom part is really what I want you to know. MTBE or methyl tert butyl ether. It's an ether, so it contains oxygen, and it's added to gasoline to raise its octane number. It's good for your car. And just a little reminder, engine knocking. Engines are obviously designed for fuels to combust or detonate at a very specific point in the cycle of your engine. You do not need to know this. This is just if you are curious, what is engine knocking? This has nothing to do with chemistry. This is more about cars or vehicles. But engines there, the fuel needs to detonate at a very specific point in the piston cycle. The detonation, the energy created from this combustion is what gives your car kinetic energy. So if you have a lower octane fuel in like a sports car, right? So you're driving around a Lamborghini or some high performance engine, if that fuel doesn't detonate properly, it can mess up the timing, and you might feel or hear a little kickback because of the messed up timing. That's what knocking is. The fuel isn't combusting at the proper point in your cycle, which causes this kind of kickback. So, if you were driving a Nissan Sunny, it kind of doesn't matter what kind of oil or gasoline you put in your car. Like back home, I have like a little Toyota Corolla. I just put in the cheapest gas I can. I don't care about it. It's like 10 years old. But if you were driving, a Bugatti or Lamborghini or Ferrari or something, you'd use the high performance fuel. Besher, you sent me a message. The last 2 weeks are already uploaded to YouTube, so the videos are there. If you can't see them yet, YouTube is just processing them, but they are there. Let me show you actually, if I can find it. So, if you go to I'm going to share my new screen here. If you look at my YouTube, you can see here. Let me go to playlists. I'll pick Chemistry 2420, of course. I'll pause this. They're all uploaded. You can see them. So even week 13. Let me pause that. Week 13 was last week. Week 13 is right here, already uploaded. All right, so Bashir, that's already there for you. Okay. Thanks, no problem. Okay, so that's it for me today. If you guys have any questions, let me know in the chat. Other than that, you're good to go. There's really one more little thing I'll explain on Wednesday, and then we can begin review. Don't forget tomorrow about your lab. It's our last lab. It's on campus. So I'll see you guys tomorrow. Do not forget. I'm going to make a D2L reminder right now. Okay, any questions? Have a good day, Niam. Anybody have any questions before I go? Okay, that's fine. Saif, that's fine. If you have an appointment and you have a note, that's perfect. That's no problem. Okay, so you will be excused. All right, guys, no problem. Thanks, Abdulaziz. I'll see you guys tomorrow. Thanks, Saif. Perfect. I'm looking forward to seeing you guys tomorrow, even though it's 7:30. But we'll get that lab over with, and then we're done. All right, goodbye, everybody. See you tomorrow.